All right, so I'm going to go ahead and pull up the review session here. Oh, they're just saying something about my cell phone. I'll try to call Shannon one more time. I mean, thank you.
I sent Jennifer my study guide. I don't know what
Geography, theology. This is Jennifer.
Oh, hey, Jennifer. Looks like the person's just there.
Okay, great.
Yeah, I think that they just needed to turn it on. All right, thanks.
And your test is Thursday?
A Tuesday, next Tuesday.
All right, thanks.
Okay, thanks. Bye.
Bye.
All right. Hey, how y'all doing down there? Good. Yeah, I think sometimes it just gets turned off or something, and so we could actually see and hear you guys, but you couldn't hear us until they turned it on. So we're all connected now, and what I've done is downloaded the review guide here. We're going to go over this for the first 15 or 20 minutes of the class, and then we'll do the lab, which is going to be on hydromodeling. And I'm not exactly sure what will happen for the test, but we'll figure that out. I know there will be some times when I actually teach from the coast, but I think wasting that on the test day would probably be not as productive as coming down there on a lecture day. So what we'll do is try to find somebody to proctor that exam, and we'll also call in. So we'll still be connected like we are today on Tuesday between you and here in Hattiesburg. And so if you have questions, you'll be able to ask them through the thing. But all right, so I've written a good portion of the test, enough now that I know what I should include on the exam sheet here. And if you go to the page, make sure you press refresh. You'll be able to download the study guide. And so I have listed. I just tried to follow it through chronologically on the review guide, the way that we covered in class. And so up here, the first item there just says raster basics. I'm looking for the very basics. These are things we likely covered in the first course, but what I'm talking about are what is a raster, what's cell size. So a raster is an evenly spaced grid of numbers that represent something on the Earth, and the cell size is the amount of space that it takes up in real life, because it's a model of reality. And then the value is the value at that location, and it can be an abstract idea. It doesn't have to be a thing that actually you could see if you got there. It could be something like population density, or it could be elevation, something that actually does exist. It could be land cover. But in the grand scheme of things, it boils down to a number at every single center point of each grid cell. And then we talked a little bit about raster to vector conversion implications. So what you should know there is that converting between raster and vector will always introduce some error. Okay, it's always going to introduce some because of the nature of taking lines that have vertices as their definition, converting them to raster. You're you're going to have to fit into that that grid pattern. So you're always going to lose something. Of course, then the other thing that I want you to remember is that the trade-off there is that we could make our grid cells smaller and smaller, but our data storage requirements would go up and up if we did that. Okay, so those are the trade-off on the raster to vector conversion implications there. We talked about the very first week, go back to that, we talked about a number of different types of models. So you should be able to know what a scale model is, a natural model, mathematical, conceptual, and then separate from that, you've got deterministic versus stochastic. So deterministic model, or most of the models that we've done so far in this course, where you run the model, and as long as the input parameters are always the same, the result will be the same. That's a deterministic model. So you run it through, and you get the same result with the same inputs. A stochastic model will be has some random element, so that when you put information into it, you can get a different result each time. We haven't really done that yet. We'll do a few of those towards the end of the course. Okay. So explain the different types of raster map algebra functions. I should have put the word functions there, but we can categorize raster map algebra functions into these bins. Local is one bin. Should have maybe written that as one. And then focal and neighborhood is another type, another bin. And then zonal and global are really two different variations of the same thing. So a globe, I don't think EA even asked about global for sure on the test. I'm pretty sure I don't. But a global is just a zonal operation that considers the entire raster. Okay? The entire raster is a single zone. And a neighborhood function, obviously, you need to know how a neighborhood window, what it does, how it works. And in fact, later on, I actually say, what do neighborhood operations do? Be able to calculate some simple ones by hand. So if I ask you to calculate the neighborhood mean for a particular window, you're just calculating the average. So you need to be able to know that. And then also, if I gave you a specific, very simple kernel, like the one that we went over, it just has maybe a 1 on one side and a -1 on the other, you need to be able to calculate the output value for that, which would basically just be subtracting the value on the left from the value on the right. Okay. All right. Okay, so let's go back up to where I was. So we were on there. Basic raster operations and overlay. We covered in class a number of raster operations. We categorized them out like by arithmetic and Boolean operators and simple mathematical operations. So you should be able to do a simple, like if I say this is grid 1 and this is grid 2, we're going to add them together, produce the output. So the output would be the addition of those two grids. Or something that would be a little bit more complicated would be if you skip down now to a couple where it says conditional operator. So if I had a conditional operation with a simple, maybe 3x3 grid, you should be able to say, okay, well, if this was the conditional statement, what would the result be in that grid? So if I said this grid has to be greater than 5, otherwise give it a value of 1, or if it's not greater than 5, get a value of 2, then your output, you should be able to look in there and find the ones that are greater than 5 or less than 5. All right, so how would I study for that type of thing? We'll go in and look at the slides first of all, and then also you can look at the ArcGIS help. The ArcGIS help is very good, although those aren't really specifically ESRI concepts. They do explain them pretty well in the help for the conditional operator. All right, going back up now to capability suitability modeling. What's the goal? It's to find areas of the Earth that are capable or suitable of sustaining a certain type of activity. We can apply them in all sorts of different, there's all sorts of different applications, socioeconomic applications, and also, biological or environmental applications to capability suitability modeling. So, what I want you to go back and study is how the combination of the risk factors, how they can be combined. We covered 3 different ways in class: pass-fail screening, ordinal combination, and weighted combination. And what those basically boil down to is, pass-fail screening means that it's either passes or fails. And so if any of the factors caused a failure, then that particular thing that you're modeling, it's not suitable or capable in that location. Okay. Ordinal combination just means we add up the factors, or adding them up is the most common way. And then weighted combination means we add them up, but we multiply them by a weight before we add them all the way up. So those are the differences there. All right, cartographic modeling. Cartographic modeling, what I want you to be able to there is, I'll have a question on the test where I give, similar to some of the labs, I give a very small example of a model. Well, actually, I describe a problem, and then you have to choose the operations, and there could be actually multiple correct answers. And I'll make the example for the test straightforward. You won't be drawing a flow diagram that covers a whole sheet of paper. There'll be 3, maybe 4 steps in the process at the most. Okay, so that's cartographic modeling. Be able to diagram a simple GIS model. Okay, conditional operations. We already covered that. It's basically a special type of local operation. All right, what do neighborhood operations do? So you should be able to, we also already covered that. Okay, zonal statistics. Okay, zonal statistics are our raster operations where we're summarizing all the rasters in a particular zone, or all the rasters that are in a certain area. So the reason that we want to do that is if, like, we wanted to summarize the average elevation over a certain area, or the average precipitation over a certain area. Those are times when we use a zonal operation. So when I say applications, I want you to be able to say, okay, if this was the scenario, which operator should I use? Okay, should I use a zonal operator in this case? Be able to recognize that. Sorry. Okay. Now, the remainder of the test is kind of what I talked about when we met on Tuesday, where we stepped through a number of each lecture. We stepped through a number of different applications, and so I want you to be able to recognize the workflow for these applications. So starting with cost distance modeling, recognize what the workflow is for cost distance modeling, and then what each output represents. So you're going to start, with cost distance modeling, you start with a cost surface. Sometimes I shouldn't say you start with a cost surface. You have to derive your cost surface, and you have to derive a data set that represents the source. So you got those 2 data sets to begin with, and then you step through the process and you take it all the way to where we took it to, which was that you have the path, the least cost path. And so you need to know the steps in between that process and what the output values in each step represent. Okay. Yeah, terrain derivatives. So we talked about a few different terrain derivatives, slope and aspect, and even hillshade and a view shed. So you should know what the output values in those terrain derivatives mean. In slope, it's the the change through that particular moving window. An aspect, it's the direction of that change. Okay, kernels, how they operate, including calculating slope. So for this, you need to know that calculating slope is a moving window operation. That's how it's done. It calculates using either the 4 nearest neighbors or all 8 values. So you know those 2 different techniques for calculating slope. All right, calculating average slope using conventional methods versus surface normal approach. Here, I said, what is the difference? You're not actually going to calculate those differences by hand, but what is the difference in that? Okay, what's the difference between those 2 approaches? And then finally, the workflow for hydrologic modeling, which I hope that will cement in place a little bit better today as we go through the lab. But you need to know, again, what each output represents, starting with your initial digital elevation model, taking it through creating a watershed from a pour point. That includes things like filling the sinks and things like that. All right, so and you also need to know some basic terms that we discussed in class: pour point, subbasin, drainage system, drainage divide, and a watershed. Oh yeah, I have that. Okay, so that'll be next Tuesday, and if anybody has any questions, anybody have any questions? Turn up. I turned you all down on the coast before when we could hear you, but not. You couldn't hear us. All right. I am recording this, so there'll be there's a YouTube link of this lecture today, so you can go back and hear whatever you want to hear from it, and you can also send me an email or whatnot. Okay, so I'm gonna close this down, and we'll do the lab for today. So the lab here is this hydrologic surface modeling. Oh, by the way, I also fixed this link in case anybody was having an issue getting it. I think most everybody got it, but I fixed the link for the hydrologic surface modeling. All right, so I'm gonna download exercise 5 here, and I'm gonna take exercise 5, lab 5. I'm gonna copy it and paste it into the directory I'll work in right here, and then I'm going to open up the lab. Now, the way that this lab works is a little bit more intensive, writing intensive at the beginning, or computationally intensive at the beginning than it is ArcGIS specific. So this is good though, because it'll give you some practice for the types of things where you'll actually have to write things down for the exam there. Okay, so there's 2 parts. So that's the first part. The first part is that you're going to, what you're going to do is follow the lab through, and then you're going to do each of these steps. You're going to do each of the steps that you'll eventually do inside of ArcGIS. Okay, and in fact, you're going to load this exact data set into ArcGIS and check your work. So that'll be one way to see that the numbers that you wrote down are correct. Okay. So you're going to start out by let's say label the pit cells with the elevation they would have once the pits are filled. Yeah. So you're going to start out by filling the pits. So you're going to find out if there's any pits. You're going to fill those. Then you're going to use the flow direction grid using the 8-direction 4-point method that was in the lab. Okay, so what you're going to do there is you're going to find out which direction each of these cells are going to flow. It doesn't really matter what direction these cells flow, so don't. That's why I'm darkening them. It does matter what those values are for the flow. In other words, this one's 58. Which direction will the water flow? I can already tell you that that 58 is going to flow this direction, or maybe that direction. Okay, but you need to calculate what that is. You don't need to calculate the rise over the run for every single one of these. Okay, it's pretty obvious that it's going to be one of these two. So you just need to find out which one has the steepest slope. Okay, so you need to calculate the steepest slope. Is it this one or is it this one? Why would I even wonder? Okay, because 38 is less than 39, right? But the run here is 100 meters, and the run here is 100 meters times the square root of 2. And so you need to figure out which one of those two is the lowest. Now they won't all even be that way. Some of them will be obvious, like this. Well, this one, once it's filled, will be 37, and so the flow direction will be that way. Okay, that direction, because it's the only one that is valid. Okay, all the other ones are higher. Okay. Actually, remember, you have to fill all of these. So these two, you'd have to fill both of them to be able to get a valid elevation. So you got to fill this one. You got to fill this one. So these would both have a value of a 43 because this is a pit. If that's in fact the way that it gets out. It looks like, actually, no, you can get out this way. Okay, so the outlet is right there. The outlet is one of these two cells. So actually I was wrong. These will not be 43. So this is 39, and you have to fill those so that will still be the outlet there. Okay. So filling sink, just like in the computer, filling sinks and flow direction is an iterative process. So you figure out the flow directions, and then you figure out where the sinks are. You fill them up so that it can travel out. That makes sense? So the first process here is to figure out where all the flow directions are going. So in this case, for right here, it would be this one. This one has no flow direction because it's a pit. And so you have to fill this pit. If you fill this to 37, this one would flow that direction, but then this whole 37 would be a pit. So then the next step is to fill this up to 39 because then it could flow out in that direction. And then it looks like we've filled that pit completely. Okay. So it looks like this one would flow out this direction, but yeah. So you have to figure out the flow direction, and then once you figure out the flow direction, you can do the flow accumulation. Okay, the flow accumulation is just the number of cells upstream flowing into it. Okay, and again, you're only going to do these for the ungrade numbers. So the highest flow direction grid is going to be down here. Finally, what you're going to do is you're going to calculate the annual runoff, and it's going to be given by this function. So you're going to multiply P, okay, times 0.51 minus 336 to determine the annual runoff given the annual rainfall grid below. So this is the grid, and remember that there are 100-meter cells. Okay, and so at the end, what we want to find out is how much water is going to get to this point. Okay, marked on B. That's going to be the outlet. How much water is going to get there? You got to multiply 100 by 100 by the runoff to get the total. Okay. It's like we kind of talked about in class. All right. Now, what you're going to do is, this is the exact same grid. And this is the part I'm going to start you off with, because this is the part that involves the actual GIS. Okay. So let's go ahead and open up ArcGIS, and we're going to use a special tool called ASCII to raster. ASCII is a data format that is still pretty widely used by some people, that stores a raster in a text format, basically. In fact, I'll show you. We could open. Let's go back into the lab 5 here. If you go into the hydro lab and you open up oh no. Oh wait, that's not how I did it this time. I didn't actually. I actually had you save it so that it would be better. So these are your elevations and your annual rainfall runoff. If you take this text here and you right-click on it, copy it, and save it into Notepad, then you will have your data set that you need. And so you can save this as, I'm going to save it as elevations. I'm going to put it right here in SA Lab 5, and I'm going to call this, make sure you change this to all files and type in elev.asc. elev.asc. Save that. Okay, and then I want to do the same thing with the annual runoff. If you ever need to create a small grid or even a large grid, like let's say, in fact, this actually has happened to me before. So somebody has created a regularly spaced grid on the landscape of the Earth, but they weren't used to GIS technologies. So this was down in Central America. They had a study area in a forest, and they had gone through and plotted at I think it was 20 meter. They actually put a stake in the ground every 20 meters, and then they collected some statistical information about those areas in the forest, and they put them all in an Excel spreadsheet. Okay. Well, you could, if you figured out the coordinate system that they had used and referenced it to a real-world coordinate system, you could then convert that Excel spreadsheet. You could export that Excel spreadsheet. Okay, using these are just tabs. Okay, a tab delimited Excel spreadsheet, and then you would just have to know how many rows and columns, what the corner is. This is actually the corner and coordinates. Notice that we're going to use 0, 0. So we're not attaching this to any real-world coordinate system, and then we specify the cell size and what the no data value is. We don't have any no data values either. So I'm going to go ahead and do this again with the rainfall. So I'll call this rain.asc. Save as rain.asc and say all files. And I'm going to save this. And I'll just close this down. So I've saved those two. So you need to do that. Okay. And then if we go into ArcGIS and we hit the add data button, sorry, not the add data button, under, where is that toolbox? I said it in my lab. Okay, conversion tools, and then to raster, ASCII to raster. And then we choose that ASCII file that we just created, CSA and then choose Lab 5 and say elevation. And then I'm going to save my output ASCII in the same area, which is CSA Lab 5. I'm just going to call this elev dot, I'm going to call it elev.img. You could just write elev and it would be fine. It would save it as a ArcInfo grid. we're going to just leave this as integer because you notice that the values that I gave you were integer values. So that's fine. So here's my result. Okay, that's my result, and it's symbolized using unique value symbolization. But this is the exact same grid that you have right here. Okay, same numbers. So if I select I and I choose it, I get 38 there, 39, which are the same numbers there, 38, 39. Okay. So I want you to do the same processes where you first calculate sinks on this, fill the sinks on this, and then calculate flow direction and flow accumulation, and finally you utilize GIS functions this time to find out what the annual runoff is. So basically, you can use a zonal function to do that. You don't need to build a toolbox for this yet, unless you want to. But the second part is that you're going to do the same thing on some real data, and I do want you to build a process for the entire thing. Okay. Now with this one though, the second time through, you have a slightly different formula here. Okay, the runoff for each cell will be equivalent to the percent imperviousness. So here I just gave you the annual rainfall, okay, and I told you that the formula would be this. So the formula is constant over every cell. That was the runoff for every cell. In this one, it's going to be the impervious layer, okay, divided by 100 times the precipitation layer. It's the percent impervious. So we're assuming that everything that doesn't get absorbed into the ground flows off. Okay. It's a simplification of reality, but one we're going to use for that exercise. So there's an extra step involved in that. So you'll need to build a model for that, okay, that does this. Okay. All right. Now I'm going to show you one thing on this this model that you're going to build, but keep in mind that you're going to have what are your inputs going to be? Your input's going to be the digital elevation model and the impervious surface model. Then your other input will be the pour point. Okay. I'm gonna wipe this out for now and show you this other data that I have. See, essay lab 5. Okay, so if you go into Hydro Lab, we've got these data sets: impervious, pour point, DEM. This is the one I just created. Oh, you also need precip. Okay, so this is actually Hattiesburg, for those of you who were wondering. There's the pour point up there. The reason why I included a pour point is because if you were just to select, lots of these areas would be really small. This one will be a little bit larger. Okay, here's the impervious surface. So those are impervious surfaces. I just derived this from some land cover data. Okay, here's the digital elevation model, and here is some precipitation just for some random rain event. Okay, that I downloaded. Okay, and so that ranges from 0.94 to 1.2599. So not too much variation there, but we're looking at about an inch to an inch, and it's interpolated based on some weather stations. So it wasn't satellite sense. So based on a few weather stations, just interpolated, you can kind of tell where the weather stations probably were, and so I created that that data set. And so these will be the inputs: precipitation, DEM, impervious, pour point, and your output is going to be the amount of runoff that reached that particular location. So after you do the workflow of the hydrologic modeling, so you'll have the pour point and the elevation data as your input for the hydrologic portion. Okay. Once you do that, you have to figure out what the runoff was in every cell using this formula. Okay, what was the runoff at every cell using that formula? Times the precipitation layer. And then you could figure out what the total runoff was in the watershed that the pour point created, okay, using, what would I use to do that? We talked about it on what was the other day we met? Tuesday. We talked about it on Tuesday. If I have a watershed and I have the amount of runoff in every cell, how could I figure out the total runoff? It's a sum. What type of operation is that? That's the kind of thing you'll be tested on the test. It's a zonal sum, right? My watershed is the zone. What's the total runoff for the watershed? Every cell represents how much runoff per cell, and I got the total thing. Okay, now to actually turn that into a total runoff, I would need to total all those up and then multiply them by the cell size, because the cell size is the third dimension there. If I'm going to get the number in cubic feet or cubic meters, whatever, it doesn't. I didn't specify. Oh, I did. I specified meters. Okay, actually, the cell size is 30 meters, and the precipitation units are in inches. So you will have to do a conversion there. Okay, what I would do there is to convert the inches into meters, or the cell size into inches. One of those two things. Convert one to the other, and then at the end, or you could convert both of them to feet. But you're going to have to do that as part of your calculation. So once you get the total amount of runoff, it'll be in just inches. Okay, that'll be that dimension, and you'll need to multiply that times the cell size times the cell size, the square, because cell sizes are square. So you've got 1 inch times 30 meters times 30 meters, but do the conversion first, is the way that I would do that. Okay. All right, just a second. Okay, I thought Jennifer was sending me some news about the proctor for the exam on the coast, but she hasn't quite figured that out yet. All right, are there any questions here? I think as you work through, you'll kind of see what the result should be as you work it through by hand. Now, you could, if you wanted to, and if it helps you, you could actually do the steps simultaneously. In other words, you could try to figure out what the flow direction was, and then run flow direction and back and forth. Okay? And that's fine. So whatever method works best for you is fine with me. All right. Now this one. This particular assignment actually won't be due for 3 weeks because of spring break. Well, so it's not due next week because it's not due next week. It's not due the week after because that's the middle of spring break. So it'll be due the week after that. That doesn't mean that you shouldn't at least get a good start on it today in order to understand the values that you're going to. In fact, just to make sure everybody knows where we're coming from here. Oops, this is previous slide. Let's go back and look at courses, CA, essay, lectures. That's the last lectures. Oops. Labs, lectures 6. Okay. I will actually want you to assign numbers, not just say that the flow is going west or northwest. So what we're looking for there is these numbers. So if it flows directly to the west, it would be 16. Because these are the numbers ArcGIS is going to assign. So I want you to be able to check your work. So you assign these values. So looking at every cell, which direction is the flow going to? Okay. All right.
And GIS always assigns it in that layout, like 128 in that corner.
It's a very common scheme. There are other.
It seems like the paper is red, the 128 was like the hospital. I don't know. It seemed like it was
Ranged slightly different.
Yeah.
Well, let's verify that because basically I want you to just to do it the same way so you can check your answer. Actually, we can go like this. Help. See which way ArcGIS does it, because you're right. It may be different. Now this is so if the reading used slightly different numbers, that's fine. But let's do it the same way ArcGIS does it, because that way you can check your answer. So that's the values that it uses. Okay. 1, 2, 1, 2, 4, 8, 16. All right. Any other questions? That was a good one. All right. I'm going to go ahead and stop the broadcast then. And I do have to talk with the student here real quick, but I'll be around for any other questions that people have. All right.